I'd like to introduce Win Schwartau, cybersecurity philosopher and founder of the Security Awareness Company, and his latest contribution to the community, Analogue Network Security. We've had 50+ years to work out the kinks in the digital world that surrounds us, but we've managed to do nothing more than tie ourselves in ever-increasingly complex knots from which we know no escape. With the concept of Analogue Network Security, Win offers a refreshing look at how we can improve the security of every system you might encounter, addressing fundamental fallacies of the cybersecurity community and contributing to the future of our field in a much-needed visionary way. After familiarizing yourself with his framework, you'll wonder why the rest of the security world hasn't already structured itself around time-based security, feedback loops, and taking an analog view of everything. So let's let Win take it from here.
Looking at the world differently is something that I have spent a good part of my career doing. And fundamentally, reason is it's not working very well. Otherwise, we wouldn't be in the security mess that we're in right now. So in this presentation, I'm going to walk you through quickly a different way of looking at security. And in order to do it, I have to take you back about 60 years to begin understanding why I look at the world so differently than everybody else. Now, the premises that we've got here need to understand is that the current security model that we are using in the vast majority of our implementations at the enterprise and infrastructure level are based upon a security model invented in 1972, designed for mainframes, single user environments, single processor environments, where the computers were locked in a room behind walls and guards and gates, and the concept of networking virtually did not exist. So based upon that, we are now still attempting to secure the world based upon this experiment, this TCP/IP experiment that we began back in the early 70s. So when we look at it, and we look at risk, we look at trust, we look at security, we don't really have metrics. And the world I grew up in was one of metrics. And I'm going to walk you through a little of the background and then look at some potential ways to view the world differently. And at the end of this session, you can actually go back into your organization and begin doing a little bit of measurement of your security profile with some very, very simple code. So I grew up as an engineer. My mother was an engineer at NBC during World War II. My father was part of the development team on radar during World War II. And I grew up as an analog engineer, being given a non-optional education by both of my parents. So by the time I was in 12 or 13, I had a pretty good idea about what systems and engineering were. My first DefCon, my first beer, allegedly, I don't even remember what was in that glass. When I was 5 and 6 years old, I made 50 cents fixing TVs, when all that meant was taking the tubes out of the back, going down to the drugstore, testing them and replacing them. And 50 cents later, I was doing good as a kid. When we built stuff, when we had to design things, we had to go into a store like this and find the little tiny bits and parts and then actually assemble everything ourselves. You couldn't go to Amazon and get a great robot or a drone kit or a Python kit in order to start playing around. We had to do everything from scratch in the analog world. Thus, my first computer was an analog computer that I built when I was 9 years old. Ultimately, I ended up in the family business, and that was in the recording studios as an engineer and producer. And when I was 16, I got introduced to this facility, and something clicked inside of my brain. And I realized that I understood systems, the patch bays, all of the controls. I had this somehow innate talent just to be able to understand systems and visualize them as to how everything went together and worked. And it was a fun career for many, many years. This is how we used to make records. That disc on the left is a cutting lathe. And that's where mechanically we would put audio into it, and it would mechanically cut the masters that ultimately became vinyl. So again, this is all analog and a combination of mechanical and electronic systems. On the right, that is Robert Moog's early synthesizer that was down at Hendrix's Electric Ladyland. Again, a complex system. That was how we made synthesized music some almost 50 years ago, and that was all that we had. When we were doing TV and movies, we would have to synchronize the audio and the video so that the voice sounded and looked appropriate at the same time. Or when somebody, the drummer hit the hi-hat, you would see it and hear it at the same time. But when things didn't work, we would have to manually use a setup like that on the right and manually control the speed of the motors in order to be able to make the synchronization work. So again, I looked at the world and grew up with it in a very different way, which was all about the analog process, not a digital process. So in '83, I said, I'm going to go become a security expert. And on the right was the only thing that existed was the Department of Defense's specifications and guidelines on how to make security work, which was not terribly effective outside of a few mainframes here and there. As PCs got into play, as networks and Novell got into play, nothing was working, and we were guessing every inch of it. So I had no degree, no certifications, no credentials, but this was so far in the early days of security, none of us knew what we were doing, and we were just absolutely guessing. So in the early days, I started really thinking about how bad things could get and wrote a couple of books on weaponizing the internet. And it came about from looking at how many viruses could be released at the same time by serious bad guys. What would be the compound effect of multiple vector attacks? We didn't call it that 30 years ago, but that's what we call it today, is the threat landscape. What is the attack surface? And back in the early days when I wrote these books, it was all brand new information, and a lot of people were not happy about it. And specifically Congress, when I testified before them about an upcoming electronic Pearl Harbor, the lead congressman on the panel, who were part of the Computer Security Act of 1987, said to me, Mr. Schwartau, can you please explain to this committee why the bad guys would ever want to use the internet at all? And that was the mindset that existed back in the early 90s for many, many years. So again, I wanted to work on fixing things, and I wrote a lot of books to be able to put some ideas together. And the most prevalent one that picked up was on time-based security, which was looking at security from an analog standpoint and using time as a common metric. Time can relate to risk. Time can relate to trust factors. Time can relate to security. When we look at APTs and an average detection time of over a year, that's a time factor. And so I started examining security, looking at it from the time window in order to be able to see if there was some answers out there. So ultimately, I wanted to prove that security could be done. And everybody said, it's impossible, it's impossible. And we're going to discuss some of the ideas that I've got on how to do this, and there will be a crass commercial plug at the end of the presentation, so I'm pre-warning you on that. So it began with, for me, from a philosophical standpoint, and the number one rule was I did not want to change protocols. TCP/IP, whether we're talking V4, V6, cannot change these at the local enterprise level, at the infrastructure level, at the ISP level. So that was number one. Number two, I wanted to get rid of zeros and ones. There is no such thing as perfect security. There is no such thing as zero security. So every bit of our security in reality is somewhere between absolutely none and absolutely perfect. So this is called min-max. And again, this goes back to my analog days. in recording studios, we had min-max controls, and you've got them currently on your audio devices. You've got treble and bass controls or equalizers or volumes, and you never set them all the way to one end or another. They're never going to go infinite. It's always somewhere in between. Number two, we're trying to do defense in depth, and defense in depth we know does not work, because that's what we're doing right now. Next generation technologies are not solving the problem. So I'm suggesting we use detection in depth, and I'll show you a couple examples of this. Because our systems are so dynamic, whether we're at the code level, we're at the partner networking level, we're at the ISP level, we're at the human level, we do not use as an industry the concept of feedback. Again, a very common industry specification from engineering mindset. Also, out-of-band communication. We tend to be very bad about that, and I'll show you a couple of examples of how we can get around it. And then the key component of this is introducing the concept of negative time into our operations in order to be able to actually have some handle on what security is. So we're going to begin with time-based security, and it's a very fundamental, simple premise. Fortress mentality doesn't work. Building high walls does not work. People go around them. They go under them. The Maginot Line, the Berlin Wall, the Great Wall of China. In military history, it has never worked. However, what we can measure in the physical world is detection time and reaction time. How long does it take a sensor on a door to detect that somebody has opened that door to set an alarm? Well, it's going to be a few milliseconds, maybe a second. It's going to be something very, very quick. Also, we know how fast in the physical world reaction time is. So you go into the office, you open the door, the alarm is triggered, and you have 30 seconds perhaps to go to the alarm panel and enter in the correct code. That's a feedback loop. And it is also using an out-of-band communication mechanism between you and the alarm system, which is independent of you and the door. So we know in the physical world how to measure detection time. We know how to measure reaction time. We know how long it should take police to show up for a physical event. But we do not know for sure how much protection a pane of glass offers. It's minimal. In our world, we should be able to measure detection time, reaction time, but we do not know, because vendors don't know, how long will their protective device, a firewall, a password mechanism, any defensive technology, how long will it stand up under a sustained attack? That's an unknown, so it's an indeterminate number. Therefore, what we do know in the second line there is that our detection time and our reaction time equals our exposure time. So if you have, in the physical world, a jewelry store or a pawn shop or something with a lot of valuables in the window, the glass window itself provides minimal amount of protection. Less than a second, depends how big a brick you've got. But we do know that the detection sensor for the alarm should be very quick, and the reaction should be some amount of time to call the police, and that'll be 90 seconds to 3 minutes, perhaps, in a good environment. The exposure time, then, is how much time the bad guys have to do bad guy stuff and how much they can steal. The goal, obviously, is to have your detection time and reaction time get as close to zero as possible, which then minimizes the amount of exposure time or risk that you're facing in the physical world with lost goods, and in the cyber world, how much damage the bad guys can actually do inside of your systems. One of the things to keep in mind is that data, it has a time component as well. And that final formula at the bottom is the bandwidth divided by the size of your data equals 1 over your exposure time. So we understand how to correlate now the bandwidth, the detection, the reaction, all with one common set of criteria and vectors, and that is time. So using feedback, we use it in the real world everywhere. That picture of the 2 balls, that is a governor on a mechanical system to keep the engines from going too fast. In the lower right, that's an acoustic feedback system. And when you hear feedback at a concert or in a live environment, That is too much signal in the feedback loop. In the upper right, that is how every single electronic circuit known to man is generalized and abstracted with feedback. The reason for feedback is it controls and minimizes and chaos from the system, whether it's physical, acoustic, or electronic. So using feedback is something that works very, very well in the non-cyber world, and we have to start taking a look at how are we actually going to start implementing that ourselves and what sort of value it brings to the proposition. In the SCADA world, everything is based upon feedback mechanisms. The largest one in the world is the Dutch system of dikes called the DeltaWorks, and there's thousands and thousands of sensors that measure water temperature, salinity. It looks at weather conditions and adjusts the balance of the entire water system of Holland using feedback. We don't use feedback in our world. But again, keep in mind that with a SCADA system, there's no binary controls. It's all an analog somewhere between greater than 0 and less than 1 with our minimum, maximum conditions that I want to apply to cybersecurity. We live in a feedback-driven world. Everything around us, thermostats, toilets, they all are based upon feedback, and now we're trying to apply them in cyberkinetic systems, such as with driverless cars, robots, and drones. But there's some other problems in there that we will address a little bit later. As neural networks become more and more popular, these are all as well analog processes that emulate the way the brain functions. And these decisions that we as humans make are never 0, never 1. They're always somewhere in between. And if you notice the bottom, the updating algorithm, that is how we change our decision making, whether we're humans or in neural networks as we're applying them to AI. Again, no hard 0, no hard 1s. So where do we have it in our world? We don't. We move data back and forth without having recursive feedback mechanism controls. We use static controls, and that is part of the reason we're having such trouble today in our world and why so many things are going wrong. So network security is a bear, and the reason I use this picture is who is going to get eaten first? Only one guy has to run faster than the bear. I have to run faster than you so that you get eaten by the bear, and this is exactly the way that feedback mechanisms work for success in the physical world. It's called OODA loops, and it was developed for aerial dogfighting. And the object was survival in an aerial combat. And Colonel John Boyd developed this, and it's called OODA. So in our world, the adaptation would be observe, which would be detection, which is observing your environment. Now, the next is orient. How do you contextualize that? What does it mean in the context of your environment, physical, human, or cyber? A decision that is made, that decision can be human. It can be done with neural networks. It can be done by policy-driven mechanisms and controls. And then what's the action taken? The orient, decide, and act are all part of the reaction. So the OODA loop is a simple way of looking at detection and reaction with the goal being make it as fast as possible with time approaching 0. And the premise is get inside your adversary's decision loop. And if you are in an aerial combat, if you're faster than your adversary, you're going to win. Making a system a little bit more complex, this is how the OODA loop works, whether we're talking in the combat realm, the cyber realm, the physical ICS SCADA realm. The more feedback that you have with the more input and varying conditions of your dynamic system, the better off that you're going to be. So we use the same thing with security awareness. In this case, we're using positive feedback with OODA loops. We want to get the mindset operating with the security awareness so it's automatic and as fast as possible. If you see something wrong, do you want your users to wait an hour? No, you want them to do it really, really quickly in order to shrink that loop. You want to squeeze the OODA and make the detection and reaction process as fast as you possibly can. Now, one example of this is something that I actually use, and I'm sure many of you do with your bank. And for me, it's mostly on mobile banking, and especially with a new device that the bank may not recognize. So I initiate a process. I want to move some money around. What does the bank do? The bank puts a delay in there, and that pause, it'll say you have 10 minutes to go to your email or your phone and get a security verification code. That's feedback done out of band. You then enter that in, and if you enter it correctly, you're allowed to transfer the money or make whatever financial transactions you may choose if you're doing a banking application. If you don't enter it correctly, or you take more than 10 minutes or whatever the prescribed policy is, you're not allowed to do it, and you'd have to reinitiate the process. So this is an example of something that we actually are starting to use in many out-of-band two-factor authentication mechanisms. Now, when I look at my wife's car, she has one of those newfangled ones with the automatic collision avoidance system. Now, a lot of people start believing that the collision avoidance system is going to solve every problem for them, and I totally disagree, because while they're good, they are still not perfect. There is no 0 and there is no 1. So in this case, my wife wants to change a lane and she initiates a process, but conceptually, do you just want to assume that your collision avoidance says, no, you're good, and then you move over? Or do you want an out-of-band feedback loop to verify it? And in this case, it's turning your head traditionally, looking in the mirrors, and verifying that some Porsche isn't coming down at 150 miles an hour that the CA system is not recognizing. Humans are great at averaging. That's why we can hit a ball, we can catch a ball in the outfield, and how we can judge to avoid accidents on highways. We are averaging everything all of the time. So this is a very simple look at applying time-based feedback loops into a decision-making process, and in this case, the goal is stay alive on the highway. Now, let's add another component in here. Let's add the concept of trust. If you remember Aldrich James and Robert Hansen, CIA and FBI, they were both super high-level intelligence officers working against the Soviet Union, except they were Soviet agents. We never caught that. And that means that we had a binary trust in them. We gave them a trusted insider. Absolutely, you are completely trusted. I argue that that is impossible. There is always an exception to 100% trust. It is not binary, constantly changing over time. And in the lower left, you see that that input is a neural network or a fuzzy network or a human decision process that influences the observation and the orientation processes in the loop. So your measuring of trust, when you hire somebody, are they now a 100% completely trusted insider? Or is there some factor of maybe not in all cases, which is why measuring of trust and having a continuous updating process using feedback mechanisms, and this can be either a technical issue, it can be a human HR issue, but we have to establish that we do not have 100% trust at all times. When you connect your network to a partner's network, do you trust them? When's the next time you vet them? Do you degrade the trust over time based upon some curves? And we have the math for this, and it goes back to Ebbinghaus' work in the 1880s. We understand how degrading trust actually occurs. Unfortunately, we still treat it as a binary condition. So let's take a look at how to do a process, any process. I'm using Alice and Bob here, and this can be code, this can be humans, it can be the networks talking to each other, really doesn't matter. So in the middle, we have what's called an RS flip-flop, and an RS flip-flop is the simplest piece of Boolean logic that exists, and it represents one bit of memory. And the Q there at the upper right is either a 0 or a 1. So when Alice makes a decision, she changes a condition, a control. And again, Alice could be a hunk of code, an API, a human decision, makes no difference. We are going to change the output queue. It's either going to go to 0 or 1 based upon Alice's change. But what we're also going to do is begin a clock and tell Bob, hey, Bob, you have 1 millisecond, you have 3 seconds, you have a week, you have a day, 3 hours to agree with Alice. Otherwise, Alice's decision will be revoked. Now, what does this mean? The truth table on the lower left is an analog-based Boolean truth table. And what it says is that we can set through policy a verification process of code based upon time with human interactions, making a real change to a system where it's a real live Alice and a real live Bob. How often do we need to revet our connections and partnering networks? This is the fundamental circuit that is behind analog network security and time-based security, because every single bit of the time that is set is done based upon policy. And that is how we can begin to control the detection time, reaction time, and put it into an implementation that will actually give us a higher level of security. So the detection in depth, inside that engine, it's a GE engine. We all fly on them. And inside of there are over 5,000 different sensors. And the reason they're there is to be able to help predict failure. So we know how many different types of detection systems there are in the physical world, in the human system. What we're beginning to learn now is, from an architectural standpoint, how many there should be inside of our cyber systems. Again, we have the analog, we have the models, and we just have chosen not to apply them in our world. So the first thing that we want to be able to do, and you can go back and do this at the end of this session, is can we actually measure the amount of security that a black box has? And in this case, a black box is some detection system. It could be malware, viruses, IDS, IPS, intrusion, any black box detection system. Now, we know, or should know, what good traffic can go in and come out unfiltered. The vendor should know this, and enterprise architects should know this. We also should know what hostile test traffic should look like that would cause, hopefully, the black box detection mechanism to say, wait, this is bad traffic. So in this case, the measurement of this black box is very, very simple. We're going to start a stream of good traffic into the black box. Then at one point, we're going to say, let's see how good this black box is, and inject known hostile traffic into that same data stream. What we're also going to do is begin a clock, and that clock is in the middle right of the drawing. When the black box mechanism detects what it should detect at the hostile traffic, it stops the clock. What does that tell us? That tells us a hard number, the detection time. How long does it take to actually detect a bad event that the vendor says we should be able to do? Now, you can code this yourselves. It's about 8-9 lines of code. Start a clock, stop a clock, and measure it. We're beginning to now start understanding the answers, and it's a simple bit of calculus up on the upper right, where all we're trying to do is get that limit function to approach 0. Speed it up as much as we possibly can. So does the black box system perform good? Does it take a minute? Does it take a second? Does it take 30 milliseconds? Does it matter what kind of hardware platform it's on? All of these variables now can actually be measured. Now we can take the same thing and add another component. We add a second clock, and after the detection is done, the first clock stops. We understand detection time. Starts a second clock, which is where the reaction matrix and process come in to remediate and fix the problem. We now have the math to say how long detection time and reaction time is with your existing situation, with your existing mechanisms. We now can actually understand and measure the exposure time for a piece of your process. Again, whether it's code, it's operational, it's human interaction, makes no difference. It's an abstract level of the way to look at these things. Now, some people say, let's combine two detection products because we're going to be better and our security will go up. That's not always true. And I've seen too many implementations where the architectural decision is, if black box A detects something, cool, but we're also going to detect black box B, and whichever one detects it, we'll go with that. And that is called an OR, and that's the gate on the lower right. But when you do the math behind it and we understand the probabilistic aspect of detection, my security actually goes down by doing an OR gate. What we need is a complementary agreement if you're going to use two products. So black box A and black box B must agree in order that to have a higher level of determination. And if you look at the math in the upper right with the AND gate, we now have 2 orders of magnitude greater confidence in our decision in this particular black box detection. That is a significant increase in the amount of security that we can do today with existing technologies by merely combining them in the correct way. Now, when we look at data exfiltration, that's always been a problem. That's how the bad guys get stuff out. Like 200 or 300 days of waiting from APTs is just entirely too weak for what we need. So in this case, we want to limit that if possible. So the SMTP request will come from Alice, and it'll set a toggle to a delay line. Now, in the SMTP traffic, it's going to go through an SMTP detection mechanism of some sort that we currently have. And it'll say, do you really want to send financials to everybody in your contact list? Do you want to send all the competitive information you've got to your competitors? We all make mistakes at SMTP, and we understand how the SMTP filtering is currently done. So once we measure that SMTP filtering and detection mechanism, as on the prior slide, all we have to do is set a policy and create a delay in that signal. So we delay the SMTP traffic some nominal amount of time based upon the measurements of the SMTP black box detection, set a feedback loop based upon that amount of time, and wait for Bob's approval. In this case, Bob's approval would be that the detection mechanism is saying this is all good, all fine. Alice, your email can go. It may go 100 milliseconds later, may go 30 seconds later, but in the SMTP world, we really don't care that much. In this particular case, it's all policy driven. The time is policy driven based upon the measurements of the actual SMTP detection mechanisms themselves. And using that math, we should be able to see 2 orders of magnitude increase of security versus just using one system by itself. Oops. So measuring phishing. How good is our phishing? How do we stop phishing? And again, here is users click on something dumb. How long does your phishing detection mechanism take? Well, we all use Web of Trust. There's some amount of time with that. There's other mechanisms for enterprise determination of whether something is likely to be phishing. Again, it's a black box detection mechanism. We can measure that. How long does it take? We introduce a delay line. User clicks on something, hold on, we want to delay it, got to go look it up, sandbox it, whatever, and then make a go, no-go decision. How long does that take? This is going to put pressure on the vendors to make sure that when they do their analysis at the detection point, in this case for phishing, it is as fast as possible so that the user experience is not interrupted. We have the technology to do this if we re-architect it slightly on the outgoing and using enterprise bus controls, API controls. Re-architecting this does not affect the existing TCP/IP infrastructure, but can significantly increase the odds of catching and reducing the amount of phishing. Now, when we have our black box detections, we have reaction remediation going on. But let's take it to another level and add a distinct out-of-band communications channel through a translator, and that's the reaction matrix format. So just to be able to communicate back and forth, and that's not a terribly different, it's no more really than doing APIs with a custom type of protocol. So when we look at, for example, DDoS and spam, what have you, again, we know what good traffic is. We should know what bad traffic is. We can measure the black box DDoS detection mechanism and then introduce the amount of time that's needed for the reaction module to be able to have the traffic go out. Again, 2 clocks, we understand how to measure it now, and this will give us the reaction process to be able to have the traffic going in delayed by the appropriate amount. Now, when you've got the enterprise all the way on the left, we have the traffic coming in that says, hey, I've got a problem here. I need to talk to my next hop. But my next hop, the ISP, that channel is often filled with bad traffic, overloaded traffic on the control signals of the TCP/IP channel. So we need to do something additional here. And this is what we end up looking like. This is a peer-to-peer network. This is what the internet looks like. It's looks like many enterprises internally. All we're doing is setting a detection reaction interface through an API into the reaction matrix, CNC, control and command, which is then policy driven. So any communications that need to occur through any of, in this case, servers, or we can apply the same construct and architecture to ISPs, we have an independent communication channel that when something goes wrong with the primary communication channel, the security channel can help. And so in this case, when we've got an overload of, in this case, DOS traffic between the enterprise and the first hop, if you're getting DOS really badly, your remediation controls are not going to work, which is why using an external reaction matrix policy over a separate out-of-band channel will help. Now, when we take this and apply the same logic, the enterprise will say, I'm getting DOS. It'll talk to the first hop, and what are ISPs really, really good at? Filtering stuff. They know how to filter. So your primary ISP will be told, hey, I'm getting this bad traffic, get rid of it. Thank you very much. Now, ISP 1 ideally would want to get rid of it, filter it there, but in this architecture, they can talk to their peer-to-peer ISPs and say, hey, we're getting some funky traffic. I see it coming from ISP B, but I'm going to let you all know about it so that if you see it later on, you can do some pre-filtering. Now, what happens if ISP 1 talks to ISP 2 to ISP 3 to ISP 4? We then are able to track back the source of the DDoS attacks to some point, depending upon the level of obfuscation that the bad guys are actually using. And this is all done with a simple API detection reaction matrix that is done out of band, communicating with the existing filtering mechanisms. If everybody on the whole planet, every ISP did this, what's going to happen with our DOS and DDoS problems? They are going to be minimized incredibly. Same thing with spam. Spam is the same issue. If I'm getting a lot of spam, I want to talk to ISP 1. ISP 1 will want to talk to the other ISPs, and we can start tracing it back to the source, depending upon level of obfuscation. Again, what does this do? This, in conversations I've had with the various ISPs and carriers, can potentially save between 90 and 97% of the traffic that is garbage on the internet today. So security can be measured, and we have to begin with measuring our detection and reaction processes to mirror what we're doing in the physical world, and we can do it in our world. We've got plenty of Maginot lines out there, but we don't have a comprehensive solution that allows us, and this is not a product pitch, this is pure architecture. I'm not selling it or building any products. We have to re-architect the way that we look at things to emulate the ICS and SCADA worlds and physical engineering worlds to be able to have some hope here. We have to get rid of infinity. That's why we use feedback. Without feedback, we end up with squeals in the audio world. We end up with electronics that don't work at all, and we end up with runaway trains and engines. So we have to tie all of these together into a comprehensive model that I call Analogue Network Security. So what can you do now? You can go measure your detection processes. Go put one on the bench and play with it. You can measure your reaction process. If it's fully automatic, how long does it take? If it requires humans in the process, how long does that take? How does Bob have to be sitting at his desk? How long does it take to reach him if he's on vacation? The other backup processes. Unless the remediation reaction process is well spelled out, we're going to continue down the road that we're in right now. You can measure your vendors. If you've got 2 antivirus solutions or malware detections, measure them, compare them. We're just starting now to get some idea of how different some of these technologies actually are. Set up a test bed. Everybody's got laboratories and friends of people with laboratories. Go measure it. Take a look. Then ask your vendor. When I talk to vendors about this at shows, they do not like these questions because the answers are going to start digging down into where a lot of the problems are today. We've got to get feedback as part of the intrinsic mechanism that we use. We have to start using time as our fundamental component because time equals a measurement of risk. Time equals a measurement of trust. Degrading trust over time. We cannot assume that trust is going to remain the same, static for long periods of time. And we have some processes, we have some ideas on how to do it. And this is where the crash commercial plug comes. There's a new book I've written on this that gives you all the schematics, all the mathematics on how to begin actually doing this stuff right now and trying to help and prod the vendors into building next generation stuff using out-of-band communication, using feedback, using OODA iterative loops in order to optimize performance and grab a handle on security. Thank you all very much. Everybody have a wonderful week.